Thank you. Today's What Physicists Do speaker is Dr. Yiyang Li of Sandia National Laboratories. That's a federally funded research and development center. His Bachelor of Science is from Olin College, and his PhD in Material Science and Engineering is from Stanford. Dr. Li is a Truman Fellow at Sandia, working on developing smart materials, as it's called, whose properties are changed through electrochemistry. I reached out and was asking for speakers, and his former advisor said, I've got the student for you. He's my former student who's off at this prestigious Truman Fellowship at Sandia Labs, and we're just really proud and happy to have him here. So let's give a warm welcome to Dr. Yiyang Li.
Thank you very much, Scott, for the introduction. So the topic of my talk is how we can store energy and information using this mechanism called electrochemical ion insertion. And my work is broadly targeted towards developing energy efficiency and renewable energy for a changing world. So I'll give some motivation. So this is a chart of the relationship between carbon dioxide, methane, and the global temperature. So as you see, in the past 500,000 years, there's a very strong correlation in the temperature and in the amount of greenhouse gases. Currently, we're above 400 parts per million carbon dioxide up here, so it takes some time for the temperature to catch up with the carbon dioxide, but it really shows how we're at unprecedented levels of climate change. If we look more specifically, climate change isn't something that will happen in the future. It's happening right now. If we look at the past anomaly in the temperature in the past 100 years, we see a steady rise in the temperature up here of about 1 degree over the historic average. As we see, there's one year, 1998, that was an El Nino year. It seems to reach a local maximum then, but it seems like we have easily overcome even the 1998 global El Nino. So in 2015, the Paris Climate Accord was an agreement by the industrialized as well as every nation to voluntarily reduce their carbon emissions. The goal, as illustrated in this consultancy chart, is to reduce the carbon intensity by 3% a year. So this is the amount of carbon dioxide generated per unit of economic output. Unfortunately, to reach our global carbon budget, we need to double that rate at 6.3%, and the business as usual, which in many ways is the current business we're going right now, might be just 1.3%. So we're really unprecedented territory. We might spend our entire carbon budget in just 20 years. So in order to try to meet our global carbon budget, to try to stay within the realms of a 2-degree rise in global temperatures, which most people think that's something we can adapt to, we need to adopt and develop new technologies. So the clearest success of clean energy technology today has been in the generation of renewable energy, such as solar and wind. I'll discuss more about our successes here. However, clean energy technology doesn't end at renewable energy generation. It doesn't end at renewable electricity generation. We also have to think about ways to store this energy. So I'll be discussing how we can store it in batteries. It also entails developing ways of using energy more efficiently. So the success in this field is in solid-state lighting or light-emitting diodes, which have basically replaced the incandescent light bulbs that, I don't know, maybe some of you have never even seen in your life. But some of them will also be discussing how we can do computation more efficiently. So a lot of the energy we save by switching to better lighting, we end up spending by mining for bitcoins and other forms of inefficient uses of computation. We can also think about resource management, how a lot of these new technology will require resources that previous technology doesn't demand much of. It requires new types of metals, new types of minerals, and we should think about how we can ensure that we have a steady supply of these minerals as well as ways of recycling them so we can have a good second life out of these technologies. And finally, if you want to work on something really hard in your career, you can think about how to try to take the carbon dioxide from the air and put it back in the ground where it deserves. It's really hard because of the economics, but if we aren't able to meet the 6.3% decrease required, it would seem like this is the only path towards staying within our carbon budget. So this is really hard, so I won't be talking about how we can reduce negative carbon emissions, but maybe one of you in your careers will be able to tackle these challenges. So the topics I'll be specifically talking about is on batteries and on neuromorphic computing. So before that, I'll talk a little bit more about renewable energy generation. So the prices of renewable electricity has plummeted over the past decades, or even in the past 10 years. So in the 1970s, when solar cells were just starting, we're using them to ensure that our spacecraft will have a sufficient source of electricity. We're looking at about $80, almost $100 per watt. Now we're looking at below $1 per watt. Last I checked, the number was below 50 cents last year. So this technology has really plummeted in cost, and significant because we only need about 500,000 square kilometers of land in order to generate all the energies that we need for all humankind. If we think about how much land we use for agriculture, we use much more than that. If we think about how much land we use for golf courses for our leaders to relax, we're looking at about 10% of the land used for golf courses, 10% of land used for solar needed to meet all solar energy demand is currently being used for golf courses. So it's not a lot of land, it's about the size of the state of Arizona or the nation of Spain. Currently, renewable energy has been very cost effective. So perhaps we heard that renewable energy is more expensive, it won't be competitive in the economic landscape, but most of those are based on past data that are not up to date with the plummeting costs. So we look at renewable sources at the top, we see that some of the more important ones are solar here. Utility grade solar, which comes out to be a cost of about $50 per megawatt hour, or about 5 cents every kilowatt hour. You compare those with conventional sources like coal, which is about $100 per megawatt hour, which explains why coal is struggling today and asking for a bailout, and it's very competitive even with this most efficient natural gas, which is this combined cycle program here. Yes?
Dr. Li, when it says levelized cost, is this still just cost to consumer, or is this cost when you take into account what carbon is doing to the environment?
This is not that's a good question. This is not taking into account any externalities. It's not taking into account any subsidies. But on the flip side to that is that because solar and wind are less reliable, so if you don't take into account the environmental costs, what you can produce that's variable is generally less value than you can produce something on demand that you need. So that's the argument against the cost of solar electricity right now. So even though right now it's lower than that of these sources, there are still some benefits to using these conventional sources of power. But nonetheless, we're at a great spot now in that the cost of renewable energy is less than that of conventional sources. And however, one big caveat is that because renewable energy is intermittent, we need to find a way of storing it. And the cost of storage has increased the cost of these renewable energies. Nonetheless, these renewable energies are making a great dent in our distribution of carbon dioxide. It's already significantly reducing that in places where it is widely adopted. So this is the emissions of the United States. So we see currently we use about 28%, so a little under 1/3 of our carbon emissions come from electricity generation. This is already advanced from 2005, where nearly 40% come from electricity generation, and much of that, in addition to renewable, is a shift from coal to natural gas as a result of fracking. But if you look at the leader in the United States, which I'll present as the state of California, we see that the electricity we use is only about 10%, the carbon emission from the state of California, only about 10% come from electricity generated in the state, and 6% come from electricity that are imported from out of the state. So it's significantly less than the United States today, and even much less than the United States in 2005. And the way we get that is that we generate about 40% of our electricity from renewable sources, so this includes hydropower. So real breakdown is about 25% wind and solar and geothermal, and 15% hydropower, and 10% from our nuclear sources, 40% from natural gas, and 10% from imports. So there's no in our grid, there's no coal left in the state of California, except maybe in these import categories. And this has made a significant dent in our carbon emissions. So this is not good enough according to our state policymakers. So earlier this month, we learned that there's a SB 100, which is the act of legislature, so it's California state law, to say that there must be zero carbon from electricity by the year 2045. And the same day, to one-up the legislature, Governor Brown signed Executive Order B5510, which says that zero net carbon by 2045. Many people think that this executive order is an ambitious goal. It's more telling us where we should be, but the SB 100 is already state law. So now, in the state of California, we can already generate, in the 6th largest economy or the 5th largest economy in the world, to have no net carbon emission from electricity generation. And I grew up in the state of Oregon. It was much easier to achieve that in Oregon when 2/3 of our electricity comes from hydroelectricity. But the fact that we're able to do that in the state of California really amounts to a testament of technology and a testament to policy, to the proper policies, not just geography. However, as we see, even though SB 100 is considered a very ambitious or state-of-the-art goal, it really only tackles this part of the pie and maybe this part of the pie as well. It's a very small part of the pie, and largely because of its own success. We want to see if we can use the renewable energy generated here to tackle our biggest source of emission in California, which is transportation. Over 40% of it, and largely because we stopped using that much carbon in order to generate electricity. So transportation takes a huge part of the pie. So the most promising solution to that is a lithium-ion battery. So I have one lithium-ion battery shown here. So this stores about a watt-hour of power. And what it is you basically are able to store electricity inside of chemical bonds. So if you want to buy one of these, I saw you can buy one of these at Walmart. They cost about $2 each if you want to buy. If you want to make an electric car like the Tesla Model S, you need about 7,000 of them put together. So that's exactly how Tesla makes it. They take 7,000 of these guys, wire them in series and parallel, and put it in the base of their car and make it. Interestingly, they put it down there so that they can't flip the car over because of all the mass at the bottom. So the energy density I thought was really interesting, that the electrical energy density of a battery approaches about 3 megajoules per liter. So that number is just a number, but if you compare it to something like gasoline octane, we're looking at about 32 megajoules per liter, but this gasoline number is in terms of thermal energy. So we all know from second law, from Carnot engine, that thermal energy, you pay huge losses when you convert it into mechanical energy, whereas electrical energy, you can convert it to mechanical energy very easily at over 90% efficiency. So the effective density of gasoline, I think, for apples-to-apple comparison, might be 8 megajoules per liter. So we're already at this roughly a factor of 2 difference between the energy density of something you literally burn up and the energy density of a battery, which you can charge and discharge over many cycles. It's not quite this simple because when you have a gasoline, you can pack it really well as a liquid. It's a little hard to pack these, and at some point you don't want to pack these so well because then you run into heating problems. So there are still some balance of systems concerns with something like with the battery, but nonetheless we're looking at really similar order of magnitude numbers between gasoline and batteries. And so electric vehicles are a great way of reducing the carbon dioxide emissions. So this is a car I drive, and if we look at the CO2 emissions, we're looking at about 1/5 of that of conventional sources. And that's largely because in California, we generate so much of our energy. So in PG&E, Northern California, we generate about 70% of our energy using carbon-free sources, including nuclear. And the cost of electricity, despite California being one of the highest costs of electricity, is only about a quarter the cost of the gasoline. And that really comes because the electric motor are so much more efficient because you don't have to pay any penalty from the Carnot engine or the second law of thermodynamics. So the mechanism for lithium-ion batteries, how they work, is this process called ion insertion. So the way I just look at it is you have 2 different materials. So in this material, I call this a lithium reservoir. So this is a place where you can store a lot of lithium, lithium being very light, lithium being very electropositive on the very left side of the periodic table, so you can store a lot of energy. On the right side, we have what's called a lithium host. So actually these materials, these are just labels. They can really well be the same or very similar materials. When you connect them in a circuit like this, what we can do is we can use a circuit to tell an electron to move from the left to the right, so it localizes onto that side over there. So if you have a capacitor or electrostatic system, then you will end up building up a charge on this plate via Gauss's law. As a result, it will be harder and harder for you to move more electrons in this way, because you have to fight against this voltage, and ultimately you can't move that many electrons over a capacitor. However, via a battery, what happens is that we have an ion conducting electrolyte, so a positive charged lithium ion moves in the same direction. So therefore, we can move an electron, but we aren't electrostatically charging up this device. What this means is that we can keep moving more and more electrons from the left to the right, and the lithium ions will just follow it. So this is fundamentally how a battery works. Because both the ion and the electron move at the same time, we're basically able to move a lot of electrons, but not electrostatically charge the device. So you can basically put on the order of 10 to the 21st first amount of charge per unit centimeter. So you can get a very high doping level and move a lot of electrons, which enables you to store energy. So some materials where you can do this, for instance, you can do it on carbon, you can do it on graphite, we can do it on iron phosphate, which is the material I'll be talking about, create lithium iron phosphate, and we have tungsten oxide, which is used as generally used at electrochromic smart windows. So if you've ever been on a Boeing 787, you notice that you don't pull the shades down, but rather you press a button and then your windows turn from light to dark. So they work off actually exactly this principle. The electrons, they move the electrons around so that you can tint the windows, but you don't have to constantly apply power for it to do so. So this ion insertion in the lithium-ion battery will be described here. So if you open up a battery such as this one here, so after this, if you want to take a look at it, you're welcome to feel like that battery is already dead, so you don't have to worry about shocking yourself. Is if you look inside, we have two electrodes. So we have one material here, which is graphite, and one material here, which is lithium iron phosphate. When we discharge a battery, we want to get energy out of the battery for when we want to run our cars. What we do is that we take a lithium ion and electron out of the negative electrode, and then we put it into the positive electrode. What this means is that we're moving the lithium from the carbon into the iron phosphate. This is basically like a substitutional chemical reaction. We move lithium from one material to the other one, and we get a change in the Gibbs free energy of 320 kilojoules per mole. Whereas in an ordinary chemical reaction, we might lose this energy just as heat, which is basically what happens when you burn up a gasoline in your car. Instead, we convert this energy into electrical energy, into electrical work at 3.4 volts. The amount of energy is the amount of charge multiplied by the voltage. The charge is a charge on the electron multiplied by the number of lithium atoms that you can get. And usually when we discharge a battery, what we're doing is we're moving the reaction in the direction that I've written here. So you move lithium from the negative electrode or the anode to the positive electrode or the cathode. When you're charging, you're doing the reaction in reverse. So for the most part, we're discussing in the discharging direction, so lithium insertion into lithium iron phosphate.
Dr. Li,
Yes.
can you show that last slide again?
Yes.
You said it in a slide before, and I want to point this out and just make sure.
Yeah.
I mean, I like how clear this is, and I mean, I felt like you showed me a physical model why a battery stays the same voltage throughout its operating life, or that
Right.
we can get this sort of same current from
Right.
it.
Mhm.
It's because we have these ions which travel much more freely, and so we don't build up
The electrostatic.
the electrostatic.
Right.
Okay.
I should follow up by saying that just because there's no electrostatic buildup, it doesn't necessarily mean the voltage stays exactly constant. Because in the end, it's about the free energy, and at the very least, you have an entropy component to the free energy, so that's going to change your voltage slightly. And if we go even deeper, one way to think about it is a semiconductor band model, whereby you initially fill the lower energy levels, so the more you charge, the higher the energy levels you need to fill. So the voltage of the battery does increase, but not nearly as much as you would think in a capacitor where you have an electrostatic buildup. So everything has to come through the physical bonding mechanisms, not through this electrostatics.
Thank you.
Thanks. So my research was through graduate school was to try to understand how we move the lithium ion from the electrolyte, from the liquid into the solid. So one way is that we could just treat it as a black box and it just kind of sort of works. So as an undergrad, I was trained as an engineer, and that's the way people taught me to think, is that it just works, don't worry about it. But when we do physics, when we do materials, we really want to understand the mechanism. So kind of very schematically drawn, we can say that the mechanism are as follows. The first is that lithium must diffuse in the electrolyte. So these are liquid electrolytes, so ions can diffuse very readily in them. What must happen next is that lithium must go into the particle, so go from outside the particle into the particle, and simultaneously accept an electron. So when it accepts this electron, this is when charge transfer happens. So it goes from a positively charged lithium ion to a neutral, elementally neutral lithium. Once that happens, it tends to go around on the surfaces, so it can move around on the surfaces before incorporating into the bulk. And once it's into the bulk, it can later diffuse inside of the particle. So these solids have enough vacant sites in them that you can move solids, move ions within these particles as well as electrons, and that allows you to move the particles to charge up the entire particle rather than just charge up the surface. My research is to try to really understand how do lithium ions insert into battery particles and how does it vary through space and time. So the way we do that is we use X-rays to try to understand what goes on within these individual battery particles. So just as if there are X-rays you can use for medicine, especially when you injure yourself, we can also use X-ray to study batteries. And our technique is very similar to continuous tomography. We're taking tomographs of our battery particles to try to understand what's happening. So this is a fly-through video of a tomograph that my colleague has done over a whole battery particle that's just 10 microns. And the goal here was to try to look at the microstructure and see where all the pores of these battery particles are. So in these very neat pictures taken using a very high energy X-ray source of what goes on inside of a commercial battery particle. So
Dr. Li, this
Yeah.
is the same as the sort of green structures you were showing
that's
in that
right,
one
that's
diagram?
right, that's right. Yeah, thanks, thank you. So these are not just used for interesting pictures to cool videos, but we're also trying to learn something about the mechanism. So the process we've done is that we took our battery particles and we put it inside of a very thin microfluidic liquid cell. So basically, if you look at cross-sectional view, we put our batteries inside of this fluid channel that is only 1 micrometer thick. The reason it's 1 micrometer is because the X-ray used are very low energy, so it can only penetrate through a very thin slice of very thin amount of material. So if you look at the manual, they give basically how much time can you put your finger inside of the X-ray beam before you die. And for these energies, actually, the benchmark is 19 years. And the reason is that the dead skin cells on top of your skin will actually absorb all the X-rays, so it actually won't do anything to you. If you just go up the energy to, say, double the energy, then the lifetime is like on the order of 1 second. So these are very low energy X-rays, which is why we have to have a very thin microfluidic liquid channel. And so we're able to charge and discharge the battery within this microfluidic liquid channel, but at the same time use these X-rays to image where the lithium is going within these particles. So our work is to use these single crystalline battery particles, so they're just about 100 nanometers thick, and the 100 nanometers thick, but they're a little larger in aspect ratio. So I have these microplatelet particles. One important thing to note about this material is that it's a one-dimensional lithium conductor. So whereas some materials are isotropic, typical metals like iron and nickel, this material is anisotropic. So I have this orthorhombic crystal structure, and it's arranged in such a way that lithium can move very fast along the 0-1-0 direction, so into the page direction, but it moves excruciatingly slow in the other direction. about 10 orders of magnitude slower in the other directions compared to the fast direction. So if we look at what happens when we do the imaging, so this is one particle that we image when we put lithium into the particle. So the green means that that region is devoid of lithium, whereas red means the region has a lot of lithium. What we can see is that the lithium likes to aggregate near other lithium. So lithium insertion starts from the outside and seems to go inward. But normally we might think of this as just a diffusional process, but it's not quite so because lithium diffuses again into the page and not from the outwards in. So what's happening is that when you put lithium into this particle, it likes to be near other lithium. So lithium is attracted to other parts of the particle that also have lithium. So we call this phase separation, and that separates into two phases. So a very simple example of this might be when you try to mix oil and water, that it will tend to separate into the oil and the water phase. If you add another droplet of water, it will aggregate near the water. So this is also evidence of phase separation. So we do a post-mortem analysis. So if we charge up a battery and then we bring it into the light source and try to see what happens, what we see is that we see these very clear, sharp boundaries between where there's a lot of lithium and where there's very little lithium. However, if we try to image live batteries, if we try to understand what happens in the battery while it is being charged and discharged, we see a very different picture start to emerge. So I want to point your attention especially to the pictures on the right. So it's going to restart again, playing a loop. And then what we can see is that we don't see these clear phase boundaries. What we see is that lithium inserts fairly uniformly into these particles. So instead of seeing an agglomeration of red and green with these sharp phase boundaries as we do here, we see it go from from green to yellow to orange to red. So we get a much more uniform intercalation of lithium. So whereas if you take a dead battery, you might see something like this. When you do a live battery, we see a very different feature start to emerge. In that phase separation is suppressed when you charge this battery quickly. So in summary, these results show us that when we lithiate it quickly, we have the solid solution pathway whereby lithium insertion is very uniform within these particles. And then when we charge it very slowly, we get phase separation. So these lithium will like to congregate near other sources of lithium. The difference between these is that this pathway yields about a gigapascal stress. That P should be a capital P, whereas this one yields very little mechanical stress. So we want to reduce the amount of mechanical stress, which can lead to fraction of material. We want batteries that can undergo in this solid solution pathway where there's a minimal amount of stress in the material. So we want to engineer batteries that are able to have minimal mechanical stress to have more solid solution character. So one way we can do that is just to charge our battery faster, but we don't really want to do that because it will degrade other parts of the battery when you do that. So instead, we're thinking about ways of we can try to minimize this phase separation. So can we suppress phase separation in this material and prevent it from happening altogether? To do that, what we do is we really look back at the crystal structure of what it fundamentally means to phase separate. So this is a crystal structure of our material, kind of in an abstract notion. An important thing to note here is that there's lithium in these particles, so these represent lithium, and then there's these one-dimensional channels. So when we go from solid solution, we can imagine that lithium is fairly uniformly distributed within this particle. And we go to phase separation, what it means you have all your lithium on this side and no lithium on the other side. So for this to happen, what it means is that the lithium must be able to go from one part of the particle to a different part of the particle. However, what's also interesting in this material is that it's a one-dimensional lithium conductor. So in principle, lithium, you can move it up and down, but it should not be able to move left and right. So our goal is to try to understand the mechanism of how lithium goes from here to here, which we clearly see against the theory by which says lithium actually shouldn't be able to move this way altogether. Yes?
Dr. Li, I think I personally need one piece of information.
Yeah.
Maybe you said it, but the efficiency is coming from the less stress, and is that because you're mechanically you actually break apart these lithiation sites and you have smaller crystals and that's less efficient then,
Yeah, that's about, so the reason that the lithium likes to be near other lithium is basically when you put the lithium in, it distorts the bonding environment such that it's easier for lithium to be next to a region that already has lithium in it. So basically, the lithium, if you think about, for instance, the lithium being in this environment versus a lithium being in this environment, the bonding of the crystal makes it so that lithium prefers to be in an environment like this.
I guess if I could
Yeah.
follow up, so that's the mechanism,
Right.
but the negative result for use in batteries
Right.
when you're having this separation is?
Yes, that is an increase in the mechanical stress of the battery. Because the reason you get a higher mechanical stress is because you basically have this part of your lattice being bigger than this part of your lattice. So one part is basically compressively straining the other part, while the other part is tensilely stressing the other.
Okay, so help me one more time.
Yeah, sorry.
So I got that now,
Uh-huh.
but the mechanical stress is, what's the negative downside of that in terms of the efficiencies? Is
Right.
it actually breaking up these materials?
I see. Yeah.
Or is it that it's not efficient because there isn't as
Right.
many channels for it to
Right.
be happening?
Generally, it's one of the mechanisms by which the battery could delaminate, could potentially lose capacity over time. It's not it might not be the dominant mechanism, but it's one of the methods that you can have a battery start to fail or degrade over time. Because when you imagine you have one crystal that's you engineered it really well, and then if it all of a sudden breaks in half, it's possible that the other half of it will not be connected, so it'd be really hard to charge up
Thank
the other half of the material. But thanks for the question. So our goal is to try to understand how we can prevent lithium from migrating between channels, and I guess to make this quick is that we realize that lithium can potentially migrate in the bulk, it can migrate along the surfaces, or it can go out of the particle altogether and migrate in the electrolyte. Our goal is to try to understand which of these pathways pervade, and without going into too much detail, the pathway that pervades is the surface diffusional pathway. So lithium to go from one part of the particle to another part of the particle, what actually happens is that it can't really just go this way, but instead it goes up to the surface and can move across the surface, which forms an extended defect within the material and go into the bulk. And what we're seeing basically, the mechanism we think it happens is that our electrolyte molecules are basically helicoptering the particles from one side to another side. So when we have electrolyte molecules, the particle can move very quickly along the surfaces, and we don't have these liquid electrolyte, it actually moves very slowly. So I guess without going into too much detail, we did some reaction diffusion simulations to try to understand how this surface diffusion ultimately affects phase separation. So what we find is kind of consistent with intuition is that the lower your surface diffusion, the more solid solution behavior you're going to have. So you can suppress phase separation through phase separation by reducing the surface diffusion. And what we also find is that what we are trying to explore is that using different surfaces and coatings to try to get these materials to not phase separate through this surface diffusional process. And to summarize the results of this, what we find is that lithium iron phosphate undergoes phase separation at lower cycling rates and solid solution at higher rates, but that the origins of this phase separation and one way that we can potentially suppress it is this fact that lithium can get picked up by these electrolyte molecules and being shuttled around the surface very quickly, such that it is going towards this lowest energy phase separation pathway. So we want to suppress phase separation, we have to suppress the migration of lithium along these surfaces. So I'll be transitioning to a different topic, so if you have any final questions on the batteries work, it's a time. Yeah.
Just a comment, it seemed very interesting. You're saying you found that a process that may not be currently done
Right.
of you need to investigate coating these particles
Right.
to suppress this motion and migration of what we're calling
Right.
phase separation.
We're suggesting that this is the mechanism, and coating could be one way of suppressing this mechanism. But we haven't found a coating that works yet. So
Okay,
Like a
good.
surfactant coating,
Sorry?
like a surfactant?
Yeah, like a surface coating, surfactant coating, yeah. Definitely. Right. So the next part of the talk, I'll be discussing computing, so especially low energy computing. So for those of us that were around in the year 2000, we may have been constantly yelling at our computers when this blue screen of death comes out, and then wondering why our computers are so freaking slow. And I don't know about you, but I felt these problems haven't shown up as much. Now usually when we're complaining about our computers is when our phone is out of batteries. So basically we're running out of batteries, we can't run it. And in many ways this is, again, it's a victim of our own success. We design computers to be much basically faster than we are, so we stop complaining about how slow they are. And so now the paradigm is largely on how to make computing more energy efficient so something like this doesn't happen. So it's not kind of just a joke like in this example. If you look at autonomous vehicles today, this is, if you go in San Francisco, you may see one of these autonomous Chevy Bolts around. So it's run by the subsidiary of GM, Cruise, and they basically engineer the Bolt so that they can in principle drive autonomously. However, kind of the dirty little secret behind autonomous cars is how much energy this autonomous system uses. So if one of us drives a Chevy Bolt, we may use like 5 kilowatts of power. So this is city driving, which is where a lot of the autonomous vehicles have initial uses. But if we have the computers drive it, it may use up to additional 2 kilowatts of power. So the energy for computing, for thinking about how to not run into pedestrians, costs about the same amount of energy as it is to drive a 2-ton vehicle inside of a city environment. So this is an enormous amount of energy, which is why autonomous vehicles are all electric, or else you'll have to go to the fuel tank very often. So kind of on a global perspective, we're also using so much electricity that we're really at the risk of busting through our global energy production. So currently in about 2018, we're already using nearly 10% of our electricity just for computing. I blame a lot on the Bitcoin miners for that problem. But if you forecast it out to mid-century, we can easily break through our world energy budget just in computing if it grows at the current pace it does today. So it's essential that we have a method of doing computation at lower energy, not just so that we don't have to charge our phones very often, but literally so that we have enough energy to do everything else we need in our society. So one really powerful computing algorithm process is what we call artificial neural networks. So computer, as most of us use it, if we try to program it, are really good if you can tell it exactly what you want it to do. If you wanted to solve a differential equation like this, you can program something really quickly and you're able to figure it out in much faster than any of us can. So computers are really good when you can give it the exact instructions you want it to do. However, if you want a computer to do something like which of these image is a cat, which is something any toddler can do, a computer really struggles at that. And the reason is that there's no real clear instructions about what is a cat, right? It's like it has whiskers, but then like, how do you tell the computer what a whisker is? So it's very difficult for a computer to do data classification like this in a way that like basically any toddler, any human can do very simply. And the reason is that computers are really struggle when there aren't defined instructions for what it needs to do. However, there is the field of machine learning, deep learning has made significant advances in the last couple of decades. So we can build this artificial neural network so that a machine can learn how to do an operation through repeated training. So just like how we learn to classify objects by looking at a lot of images of objects, a lot of examples of objects, a computer can also be trained to identify what does a cat look like by showing a lot of images that are cats and a lot of images that are not cats, and be able to classify itself in these algorithms, these deep learning algorithms. So we're not going into too much detail. The way these deep learning algorithms work is that you have your input data, so you have your input vector here, and then this is your output vector. You have your input vector over here, which can be your individual pixels of your cat image, and then you can multiply it by this matrix here. So this large matrix, which can easily be over 1,000 by 1,000 in size, will transform your input vector into your output vector. And the way this works is that you feed it a lot of training examples, and through an algorithm called backpropagation, you change what these matrix weights are so that every time you train your network gets a little more accurate until it is able to do these data classifications really well. Unfortunately, whereas maybe one of us can classify something with just 5 or 10 examples, a computer still requires tens of thousands of examples in order to be able to classify it. And part of it is because it's not able to draw upon the reservoir of knowledge that we've built up, and also because computing is not as parallel or as efficient as a human brain. So this process, as you can imagine, takes up a lot of energy. We're multiplying matrices that are 1 million size. We have to go through tens of thousands of training examples. We're basically doing billions of operations in order to train this neural network. And if any of us know a little about computer architecture, doing a multiplication operation is not that simple either. It requires several steps, whereas something like an addition operation would just require one step. So the way this is typically done is through digital logic. So we basically brute force our way into creating CPUs and GPUs to be able to do these operations in parallel. So we might have 1,000 cores basically just crunching away at these operations until we train our neural network to be able to store this information, to be able to do these operations very effectively. So this is kind of a bit using existing technology and to be able to use a lot of energy, use a lot of power in order to perform these algorithms. The way we propose doing it is to use non-volatile memory to look at more analog forms of logic at being able to conduct these operations. So instead of doing these operations brute force way using digital logic, instead we create what these non-volatile memory. So you can just think of these as resistors. So imagine you have resistors at each of these networks. So if you pass in an input vector, which are your voltages, you can do a matrix multiplication by looking at your output vectors by reading the currents. So now you're doing an input and your output this way, so you're directly using physics. You're using a combination of Ohm's law and Kirchhoff's law to do your matrix multiplications rather than doing it in a digital logic scheme. This alternate pathway, we estimate, can consume 2 to 3 orders of magnitude less power than kind of this brute force way of doing computation using GPUs and CPUs. So the advantage there, of course, is that you get much lower power because you're doing everything in parallel. You really only have to do the processing at the edges of the network. So instead of doing n squared operations, you're just doing 2n operations here and operations here. So you can consume less power, and then whereas this is still used today because the technology is ready. So even though we have to pay a large energy penalty, where this technology is available in this way. So kind of another way to illustrate why these new computing architecture can do these more efficiently is that if you look at the standard von Neumann architecture, how this does computing is you have memory that is stored in representing this matrix. So you take one of our elements from our memory, then you bring it over this database into what's this called the arithmetic logic unit. So this is your processor, and then you perform the operation, bring it back along the database, and then put it back into memory. So all of your latency, your energy efficiency, your energy costs are being used to move information from this memory into this logic unit. Our alternative approach is to do the computation directly on the memory. So you're basically feeding inputs vectors here, 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 and through the edges of this network, and being able to redefine what each of these values are just simply based on the inputs that you put here. So this is a much more efficient way of doing this computation because you're not having to shuttle information back and forth. And the one way we can potentially say program this element here is you apply 1 volt, a positive voltage here and a negative voltage here. You put a large voltage drop across this device and we can use it to change the state of this device. So if we want to be able to train our networks, we need to be able to change what these matrix weights are, and then you can use that to be able to do your computation in a much more efficient manner. You don't want to build a new network every time you have a new operation to do. So kind of an example of a difference between analog and digital, we look at this goal match between Google's DeepMind AlphaGo network and the world grandmaster in this game of Go. So in the news, this was touted as a great achievement of artificial intelligence in the fact that AlphaGo was able to be the world's best player at this game. However, the difference is that AlphaGo was consuming easily megawatts of power, so using thousands of processors, and the energy bill for AlphaGo was on order of $3,000 for this operation. Whereas his opponent here uses a human brain, which is 10 hertz, and 10 hertz using about 20 watts of power, and the energy bill for him, I don't know what restaurant he ate at after, but it's certainly much less, maybe even at the French Laundry, it would be much less than the energy bill for this Google architecture here. So, and the reason the human brain is much more efficient is that we have this very parallel network of 100 billion neurons and about 100 trillion synapses. So our goal is to try to inspire from the human brain, how can we do computing, do these operations in a much more efficient manner using neural-inspired architecture that are highly parallel, non-volatile memory. So once again, we go to ion insertion as one way that we can potentially do this. And here, the goal is not to store energy in this case. Actually, we actually want to not store energy when we try to create a computer, but be able to use the fact that you can move a lot of electrons and ions into this device without charging it up, and use that to create new memory architectures, non-volatile memory architectures. And the key advantage being that you can put a lot of charge on this material without building up a large voltage gap. So this is a device architecture that we are doing. Apologize for this slide, this thing here. And so basically what we do is that it's like a field effect transistor, except it doesn't work off electric field. So it's just we call this an ion insertion transistor. And basically we're moving lithium from two materials, the gate and the channel. So whereas a transistor, you build up an electrostatic field here to modulate the channel conductance. Here we're physically moving material, moving lithium ions from the gate to the channel. And by moving lithium ions, we change the amount of electrons at the bottom here. As a result, we can change the electronic conductivity of this material. So this transistor operates on a process of moving dopants. So whereas in semiconductor world, usually dopants are something you put into your material during fabrication to change the Fermi energy. Here we're actually moving dopants in the material to change the conductivity in real time. And the way this works is that as a function of a voltage, so we apply voltage to charge this material, we can do it so that we can change the electronic conductivity. So if we increase the lithium concentration, we can move more lithium into this material and then change the conductivity, and it's reversible on the way back. And the final part of this is a switch over here. So the switch is needed in order to retain non-volatility, so that if we can close the switch, what that means is that we can isolate this gate electrode here, so your battery doesn't self-discharge. So your lithium that you work so hard to move back and forth doesn't just automatically move back when you remove the switch. So this is an example of what we have done. So we use what's called a diffusive memristor, which is this analog switch that is able to basically increase. Basically, what it means is that when you put a large voltage across it, you're able to change this device from a conducting to an insulating state. So when you put a large voltage, this switch turns on, so you can pass electrons and pass electrons through. And when you apply a little voltage, then this device starts to turn off. So what we can do is that when we just apply a couple millivolts, so 400 millivolts across this device, we're able to change the conductivity of this channel. So we're moving electrons and lithium so that we can change the conductivity of the channel, and as a result, change the state, the synaptic weights, change the weights here that we use to do computation. And it's also non-volatile in the sense that when we can shut off this switch, we can keep this device can prevent this device from self-discharging. So it's able to maintain the state even when we remove the charge from the material, even when we remove the voltage that we use to program this device. So I'll end with just the description of why this ion insertion transistor is less volatile, and I compare it to a more typical transistor like a MOSFET, a field effect transistor, which is used in every computer today. So if we think about what makes a transistor able to control the conductivity of a channel, what only happens is that you must put charge on this gate electrode. So in a field effect transistor, you directly put charge and the electrostatic field will ultimately modulate the channel, whereas in an ion insertion transistor, we put charge on the gate electrode so that we can also move charge between the gate and the channel and change the conductivity in that manner. So our retention time is basically the amount of charge you have on your gate electrode divided by the leakage current. So we can put a switch here, but no switch is perfect, no electronic switch is perfect. So as a result, we have this leakage current that goes through the outside. So the retention time is how much charge you put divided by the amount of leakage. Another way you can think about it is the capacitance of the gate electrode, so how much charge you can put on it per given unit of voltage, multiplied by the resistance, whatever resistor you put in here that dictates your leakage current. So it's just the RC time constant here. So if we think about a field effect transistor, the capacitance of the gate, if you look at just basically looking at looking at Gauss's law, we can look at a capacitance of about 10 to the minus 7, I forgot my units, 10 to the minus 7 farads per centimeter squared. So that's the capacitance of a typical gate electrode in a field effect transistor. So if you want to operate this in a volatile mode, so this isn't a lot of capacitance, we can have these memory elements called dynamic random access memory, which in this case we use another transistor here basically as a switch, and we can retain that for about 1 second of retention time. But the advantage here is that you only need about 1 volt to program this device, and so you get a low voltage but volatile mechanism. If we think about flash memory, on the other hand, the ones in your USB drives and more commonly in computers nowadays, the switch is this silicon dioxide tunnel oxide. So basically you have what they call floating gate. So this gate here is not electrically connected to anything else. It's basically completely isolated by a silicon dioxide layer. So you can create a very low leakage in this device that gives you 10-year retention time. However, the problem is that because it's not electrically connected, it's also really hard to access it, to program it. And the way that we program flash memory is that we apply over 10 volts of programming voltage in order to tunnel through the oxide, so you can force the electrons to go through the oxide via tunneling. However, this requires a lot of energy, a lot of power, and ultimately limits the lifetime of flash memory to the order of 10 to the 5th to 10 to the 6th number of cycles. What we're able to do with the ion insertion transistor is that we're able to really increase the capacitance. So on the order of 10 to the minus 2 farads per centimeter squared. So 5 orders of magnitude higher than a standard field effect transistor. And that results because we can put a lot of charge into our material. We don't have electrostatic buildup, and we're also able to put charge in the entire bulk of the material. So this is assuming, say, 100 nanometer of thickness. So depending on how thick your material is, this effective quote-unquote aerial capacitance will start to matter. So what this can potentially let us do is to have 5 orders of magnitude higher retention, but still maintain the very low switching voltage of dynamic random access memory. So it's ultimately enabled by this ion insertion technology. So our speed is not great in these materials. So because we're having to move matter, we're having to move ions through, we're looking about in the milliseconds on the order of milliseconds rather than nanoseconds in terms of the switching speed. However, if we think about non-volatile memories, the switching speeds is already on the order of microseconds. So we are pretty close to that already. And the advantage is when we do neuromorphic computing, the benchmarks for how fast we do things are not nearly as strict as more high performance computing. So for instance, if we think about autonomous cars, our cars really only need to operate about as fast as we do. We don't need cars that can work faster than we can. So and then our brains operate only on the order of about 10 hertz or so. So when we have switching speeds in the kilohertz, we can conceivably achieve similar types of behavior as the cars for many of these applications. and we're able to attain retention. So this is an example of 1 million pulses. We actually found devices that we can retain up to 1 billion individual cycles. So it is something we're working towards, but nonetheless, as a non-volatile switching mechanism, we're hopeful that this technology can make a significant impact into these next generation low power computing architectures. So in summary, what we've done is that we're able to use ion insertion for neuromorphic computing, which are able to do these operations in a much more parallel fashion and in a low energy fashion compared to conventional digital electronics. And finally, I'd like to end with this slide. So these are what I believe to be the technological challenges towards clean energy, renewable energy. I specifically talk about these batteries and neuromorphic computing, and I'm hopeful that some of us in the audience in our careers can work towards some of these other challenges, especially this really hard one of negative carbon emissions. So thank you all for your attention.
We're before 5, so I'd like to take a couple of our questions as group questions before we have the extended questions section at 5. So do we have some questions for Dr. Li?
You said that you use X-rays and a thin layer of fluid to get information of your system there. Is that X-ray diffraction, or what process were you using the X-rays?
That's a great question. Unfortunately, I deleted a slide. I tried to explain it more carefully. So I guess I'll put it back to. Sorry. It's not pulling up my collaborator's paper. Yeah. So it's the process we do is called X-ray absorption spectroscopy. So the way we think about it is that these electrons have different energy levels, S, P, D, etc. So we basically excite an electron from the 2p band to the Fermi level, which is the 3d band. And based on energy of the 2p band as well as the energy of the Fermi level, then we can have a spectroscopic signature of the absorption profile. So depending on the bonding, they will absorb these X-rays a little differently. So we found in this material is if you have a lithium on the side versus an iron, if you have lithium, you reduce iron from 3 plus to 2 plus. And the iron 3 plus has a different spectroscopic signature than the iron 2 plus. So we use that to determine where the lithium is. And furthermore, we use that we can scan it so we can get a microscopic picture of what's happening here as well.
When you say scan, do you mean change the X-ray energy?
We both change the X-ray energy, but when I say scan here, I mean we actually scan the sample. So yeah, so we do both. I have to do both.
May I follow up? Were you
Yeah.
doing tomography here as well to get 3D structures?
Yeah, no, unfortunately not. We have it's a little, we're working on doing tomography here, but it's a little more challenging. So.
And so is this done using the advanced lights? Or?
That's right, yeah, advanced at Berkeley, that's right.
Well, I think we're going to have some more questions, but why don't we thank our speaker again and let those of you who need
Flips or
Right.
or rights,
Uh-huh,
and in yours, well, the charge,
right.
which is longer term.
Well, so the retention time, it's for us, we still, in the end, we still have an RC. We can only increase the R so much, and we won't be able to beat flash memory on the retention time. Their gate oxide is just very powerful at that. But we're thinking that we are better in terms of endurance and lower power, because when you're looking at 10 volts, basically all your energy is being spent on basically charging up your capacitors and operate a flash in that manner. So that's very difficult for a flash memory to reach ultimately low energy, low power. But if you're talking about like my flash drive, I mean, if we only use it to store ones and zeros, to use it to store information, then definitely the flash drive was still the best technology that we have. Unless you need to write it so many times, like I'm not an expert on the specifics of flash, but my understanding is for some of the very high performance aspects, they don't want to use flash memory because they have to switch it so many times that the flash memory, it starts breaking down after a million switches or so. Yes.
I might have missed it, and it might be a simple question,
Uh-huh.
but you said that you were moving the lithium ions to specific places.
Uh-huh.
Is that with voltage, or how do you move it, like one charged particle at a time?
Right. So we basically move it by just controlling the amount of current. So we've developed really good technologies at measuring, controlling current and voltage. So all we do is we basically tell it we use a current source or a voltage source to move the electron from the left to the right. And then after we move the electron, the system is now charged imbalance. So then you have an ion basically follows it in order to eliminate this electrostatic buildup. So as to specific locations, we don't have a way of controlling that, which is why I use imaging to try to understand where it goes.
And as
Thank
a
Yeah.
follow-up to that, this electrolyte in the middle of your diagram, you said that's a fluid? Or-
So it can be so the first part of my talk, the batteries where we use a fluid, and that one there also uses a fluid. It's an organic polar solvent with a lithium salt, so it's just just an electrolyte. But we can also use solids, so there are solid materials whereby you can move ions through, and some of them actually have really high conductivities of ions comparable with liquids. Yeah.
I have sort of a general question
Uh-huh.
about battery technology in
Yes.
general. Are you optimistic that major leaps can be made in battery technology, that we take some of these things that aren't practical and make them an order of magnitude cheaper to do?
So it's
really change the, in other words, do we have any reason to be optimistic that
Mhm.
we're going to get new solutions to problems that are going to make some of the things that people think are really hard to do not so hard?
Don't think there are significant technical advances to be made in batteries. And the reason is we're already looking at energy densities, effective energy densities on the same order as octane. It's really hard to believe that we can go much better
I see.
than that. As far as price goes, there is still opportunity to reduce the price, which is primarily a manufacturing kind of scaling, the learning curve thing. So all technology is going to get cheaper over time. And until eventually we get to some potential resource limit that could limit the cost of the battery. But then that's again, a victim of its own success per se. And in many ways, I think the prices of batteries are actually quite low right now. So if you look at all the prices of batteries are going towards about $100 per kilowatt hour, which is one order of magnitude decrease from 10 years ago. And a typical battery at that price is really only a $5,000 price margin over basically the cost of a battery in an electric car might just be about $5,000 or $10,000 more than if you don't have the battery in that car. So, yeah.
Regarding your part of the presentation with dealing with neuromorphic architecture,
Mhm.
you showed a memristor array.
Right.
Out of curiosity, from the gates that you are working with specifically,
Uh-huh.
the memristors, do they have, does the resistance vary almost continuously, or is it more discrete between the
Yeah.
gates?
So so most of this field has been. So I didn't talk much about memristors, but most of this field, neuromorphic, has been the memristors, and part of that is since it's recorded, maybe I'll tell you later why my opinion. But the problem with the memristors is that my view is that they're fundamentally a binary architecture, that you kind of get a switching or don't get switching. So a lot of people are trying to make these analog, but what you're trying to do ultimately is you're trying to store a lot of states in the material within just like one filament. So basically you have like one atomic filament and you're trying to store 50 states in one atom. So it's questionable how that can work out. So it's a fundamental challenge with it. Whereas for us, when we use ion insertion, we're basically storing material in the bulk. So when we have a million atoms, you can imagine you can change it. You can change it pretty easily. Whereas in memristor, it's really hard to make it analog. So memristor is really great for digital though.
Excellent.
Yeah, but we use memory switch only as switches, so we use them as for the digital purpose. Other people are trying to use it for analog purposes. Great question.
I wonder if you can comment about how, I mean, this is fundamental research on something that is also, very important to industry.
Right.
For our students, can you talk a little bit about being on the sort of more pure research side and your interactions with industry and,
Right.
and how they're taking these new ideas? and
Yeah,
working
that's a great question. So our work, I guess, maybe I'll go back. We have quite a few collaborators from, or more like sponsors from industry. So Toyota, Ford, and Samsung are our industry sponsor for the battery work. And for a lot of them, it's their way of, the reason they sponsor our work is that they want to basically not miss out on some of the technologies that are out in the universities. But what we can do in a university is that we can look at some very basic fundamental mechanisms. So we're really looking at what happens within these materials, whereas the industry is you're making advances in batteries. For instance, you're really taking that technology and making it better. It's true that you are improving battery technology by 5 or 7% a year, but then when you're improving a $50 billion industry by 5% a year, that's actually a really big impact that you're making. You're really enabling these technology to be used at a variety of applications that are hopefully beneficial for society.
Thank you. Well, why don't we take our questions and do a more private thing after the talk? One more time. Let's say that.
Thank you.